Welcome everyone. My name is Ana Sanchez, and as a member of the MDPI conference team, I wanted to welcome you to this special webinar within the European Geoscience Union General Assembly and the journal Water. Thank you very much for joining us today. If you are registered to the conference, remember that you can visit our booth and chat with our representative, and I'll be sharing the link to our booth in the chat in a few moments. First of all, some consideration for this webinar. Please have your microphone off during the whole webinar to avoid possible interferences. You can have the camera on or off, that's up to you. However, I would like to inform everyone that this webinar is being recorded and it will be shared once edited as soon as possible, so up to you. We will have two main speakers today, Dr. Liliane Auwerter and Professor Helena Ramos, and the session will last around 45 minutes. If after the two talks we still have some time, we will do a brief questions and answer time. So feel free to post your questions and comments on the chat during the whole webinar. Now I would like to present our speakers. First of all, we will have Liliane. She joined MDPI in 2020 and will talk about a little bit our journal Water. She studied environmental process technology at the Federal University of Technology in Paraná, Brazil, and obtained her master's in water and environmental engineering at the University of Surrey in UK. Between 2012 and 2015, she worked at Thames Water as a research assistant. And in that year, she joined the Fluid Dynamics group at the Imperial College in London as a PhD student and graduated in May 2020. Her research focused on low friction materials for water transport. After her talk, we will have Helena Ramos, who is a professor at Instituto Superior Técnico, the engineering faculty of the University of Lisbon. She has more than 400 publications with 7 published books. She also participated in 32 scientific research projects. She has been invited as superior and evaluator of several examinations and projects, and also to collaborate in several proposals, covering contacts crossing European Union, Latin America, Canada, Hong Kong, and USA, Morocco, and Tunisia. She will be talking on the role of hydropower in the energy transition. So that's all for my part. I will hand out the microphone to them. Thank you for accepting to participate in this webinar, and everyone enjoy.
Thank you, Ana. So I'm going to share my screen now. Okay, I hope you can see everything. I'm Liliane and I am the publishing manager of Water. So I'd like to give you a brief introduction of the journal and also introduce our manuscript procedure for those of you who are not familiar with the journal. So firstly, a brief introduction. The journal was launched in 2009 and was firstly covered by the Science Citation Index in 2012. Then finally, 2013, received our first impact factor. And the journal has only been growing. We have currently a few societies affiliated with us. And currently our impact factor is 2.544, and we expect this to only increase. A little bit about the aims and scope. So if you arrived here because you're interested in the section of EGU of hydrological sciences, we cover a lot of this topic in the journal Water, including hydrology, hydrogeology, water management, hydraulics, and a few other ones. One example of the affiliated societies are the Stockholm International Water Institute, the International Conference on Flood Management, the American Institute of Hydrology, and the Polish Limnological Society. And I'm going to give you a brief introduction of our manuscript handling and so on. So firstly, I'd like to tell you about the author benefits. We are a complete open access journal. So once you publish with us, you can share the manuscript as you want, because there is no copyright constraints. We also ensure a fast publication. So journal belongs to Water is a journal that belongs to MDPI, and in general, MDPI is a fast publisher. Our manuscript processing time is around 40 days, and we have no restrictions on the length of papers, and I think also no restrictions on the number of figures and the number of tables. Our editor-in-chief is Dr. Jean-Luc Probst from the University of Toulouse, and Professor Ramos, who's going to talk after me. She's from the University of Lisbon. She's editor-in-chief of this section of hydraulics and part of our editorial board. We also have several other editorial board members from very good institutions around the world. And I'd like to give you a brief overview of how we handle manuscripts. If you are unaware of the journal, how it works. So it's just like any other peer-reviewed journal. We receive a manuscript, it is submitted, and we do a pre-check for a few things, for instance, plagiarism, ethics, and then this is sent to peer review. And all of the reports from the reviewers, they are checked by a quality control team. So every report is checked if they are really meaningful for the authors and if the reviewers are really experts in the field. So we send these reports to the authors for revisions. There's going to be some iteration there. After all of the revisions are completed, we're going to send all of this to the academic editor who's going to make a decision. For instance, it's a person from our editorial board or a guest editor. And this manuscript can be rejected. But if it is accepted, then it goes to our in-house production and publication. We also do English corrections and so on. So a lot of the work is done by us. We take a lot of the workload out from the editor and the authors to really make, so that they only make the meaningful decisions. And also have a high reach. So for instance, here I took a manuscript that was published on 16th of April, and in just 3 days, it received around 100 full text views and over 150 abstract views. So we can really reach a lot of people once the manuscript is published. And the citations have also been increased a lot in the past years at a rate higher than the papers are published. So we expect the impact factor to continue increasing. We are currently at the Q2 in water at the journal citation report. And in CiteScore, we're in Q1 in the topic geography, planning, and development. And also, I'd like to let you know that, as I said before, water belongs to MDPI, and MDPI is completing 25 years. If you want to know more about it, there is our website I'm going to show you soon, but also I'd like to show a few figures before. The rejection rate is currently 57%, which ensures that good quality papers are published. We also have around 132 society collaborating with us. And these figures are all in our website. And if you want to know more about water or to publishing water, you can submit at mdpi.com/journal/water. And if you have any questions to me, please do not hesitate in sending me an email. You can also write your questions here, as Anna said before. My email is liliane.auwerter@mdpi.com. And I'm going to leave you now with Professor Ramos. She's a section editor. She's a section editor-in-chief in our journal. Yeah.
Okay. Thank you, Liliana. Thank you, Anna. It's a pleasure to be here. Let me share. Okay, my presentation. Right. Okay. Well, the title of my presentation, as mentioned before by Hannah, is about the role of hydropower. Hydropower, it means water, okay, to produce energy in the energy transition. It is a very important issue in the next decade, and I hope you enjoy this presentation. Well, it is. I will give you a brief introduction, and it is very important, this observation. We are in decade of renewables. Let's use this opportunity to make more and more in an integrated way towards energy decarbonization. For example, we can see the installed capacity of renewable energies for electricity production worldwide increased almost 50% when we compared between 20 and 19. Despite the global economic slowdown caused by the COVID-19 pandemic, but it is reported on the statistics of renewable capacity 2021 by IRENA, International Renewable Energy Agency. The report shows that about 80% of the new electrical capacity installed in 2020 is of renewable origin, with solar and wind energy accounting for 91% of this share. These two sources were decisive for the expansion of renewables. For example, at the end of the 2020, the global renewable generation capacity was around 2,080 100 gigawatt. Hydropower, due to its reliability, ensures the largest representation with 1,200 gigawatt of power installed. But solar and wind, while more modern technologies, continue to gain ground with the correct adaptation, of course, to the current requirements. Well, these trends reflected in the IRENA report should be seen as an inspiration that needs to be continued in this decade of renewables that has just begun. And the decade of renewables between 2020 and 2030 creates a unique opportunity in terms of social development and economic growth. For example, here, this is a representation from Portugal, and we can observe from 2021, it disappeared completely, the coal power generation. And of course, the hydropower, together with the pump storage, will be essential to integrate or to make the penetration of wind and solar photovoltaics energy. In 2020, China and the United States of America were the two fastest growing markets in the installation of power plants, producing electricity from renewable sources. For example, China installed a huge value in terms of power capacity in 2020. We can see here, oops, no, what I did, okay, I'm sorry. We can see, no, I would like to have a pointer, but okay. We can see, for example, in turn, the United States accommodated around 30 gigawatts of renewables last year, also with solar and wind power installed, almost 80% more than 2019. Well, here we can observe on the top of the left, in the left top, okay, we can observe the wet month shows the importance of renewables in a complementary way, and the reduction on the market price. Here we can see, for example, when we don't have in gray the production by fossils, okay, the market price comes down, completely down, and decreases the price of the energy. It is very, very important benefit for the society. As well, we can see the CO2 emissions will reduce significantly from 2021. From 2021, we can see reduction almost disappear these emissions of CO2. Well, a significant effort is required to reduce carbon emissions generated by industrial processes and land use by 2050. Additionally, if the climate objective of Paris Agreement was raised to restrict global temperature rise to 1.5 Celsius degrees, this would require significant additional emission reductions and a steeper decline in the global emissions. Well, we can see the energy-related CO2 emissions here, reduction of around 19% by renewable and energy efficiency that will be necessary by around 2050. In this slide, we can see some key indicators to the energy transition. China is the world's largest energy producer, consumer and power generator. At the same time, it ranks top in terms of installed hydropower, wind and solar photovoltaic power generation capacity. On the other hand, the European Union, we can see in the middle of this graph, the European Union has been at the forefront of global renewable energy deployment and has played a key role in raising international awareness and advancing policy action to address the global challenge of climate change. More effort will be needed to meet long-term decarbonization commitments and would need to increase this share to 70% by 2050. As we can see here, 70 in terms of the share of renewable energy in final energy use. Well, the rising importance of solar and wind energy in the power sector is very interesting. To deliver the energy transition, the almost complete decarbonization of the electricity sector by 2050 is required. How we can do this? By using renewables, increasing energy efficiency, and making power systems more flexible. The electricity consumption in end-use sectors should double it. We can see observed in this graph. Would double by 2050 relatively to 2015 to over 42 terawatt hour, while the carbon intensity of the power sector would decline by 85%. Well, there is a relationship between energy consumption and production from renewable sources. The relationship between the energy source and the selling price of electricity also exists in terms of costs. This means the greater the representativeness of renewable energy source, the lower the market price is. We can observe in these green bars, this means renewable energy production. When we have more production from renewables, the market price decreases and decay like this. Well, so it appears a very interesting solution based on pumped hydro systems. So the challenge is focused on the using renewable sources, such as the wind and solar power, with their variability, intermittency, unpredictability, and dependence on the weather, together with solutions supported by hydropower. You can see in this figure pump storage energy solutions, okay, which the storage can be more than 8 hours or more, depending on the water volume that we can retain in these two reservoirs. And we can integrate, we can make the absorption also of these intermittent energies like solar and wind energy. Comparing with the other type of batteries that you can see on the bottom of this figure, which the storage is almost only 1 or 4 hours. Well, in many European countries, the phase out of nuclear and coal generation has started with the transition to new renewable sources, comprising mainly solar and wind for electricity generation. However, they are variable energy sources and difficult to align with the demand. So hydropower has already an important role today and will become even more important in the next decade, since hydropower can be a catalyst for the energy transition. Then, hydropower will be one of the most crucial pillars of the future electric systems, requiring for the full integration of renewables and the grid regulation, thanks to its high quality of flexibility and storage. Hydropower already supports the integration of wind and solar energy. Nowadays, we can see different systems like this into the supply grid through flexibility in generation, as well as its potential for storage capacity. This service will be in much greater demand to achieve the energy transition in Europe and worldwide. This will require a more flexible, efficient, environmentally and socially acceptable approach to the increasing hydropower production to complement wind and solar energy production. So the ambitions plan for the energy transition in Europe seeks to achieve a low carbon climate resilience future safely and cost effectively, serving as a worldwide example. The key role of electricity will be strongly reinforced in this energy transition. For example, reservoirs of hydropower plants will have to contribute more and more to the mitigation also of the climate effects as a natural battery without waste, without so many environmental impacts comparing with the other type of batteries. Europe has long-term experience with hydropower design, construction, operation, and maintenance. The know-how of the European industry, comprising manufacturing, engineering, and consulting, is strongly recognized worldwide. Hydropower is the most preferable source of energy, or at least the powerful and efficient vector for global decarbonization. Hydropower is a climate-friendly technology, preventing lowest release of CO2 and mitigating with water storage the impact of global warming and climate change. Hydropower is well suited to support the power network with flexibility and storage. It increases new renewables energy penetration, as I mentioned before, with potential role in energy transition and will result in opportunities for new developments, especially for small hydropower, medium, and until the large ones. Hydropower increases the storage capacity both in short and long terms. The investment in hydropower will be considered as a safe value in the long term. Well, the International Energy Agency recognizes the critical role of renewable and flexible hydropower in helping countries to meet their climate and sustainable development goals. Looking at this figure, we can see that the combining renewable energy resources is the best way to overcome energy shortcoming, which not only provides more reliable power systems, increasing the storage capacity, but also leads to the reduction in climate change effects. Through proper management of both resources, for example, here we can observe between wind and hydropower, and we can see in some periods of the day we have more wind available than water, and we can use this energy for pumping solutions, okay, in order to have and to put available hydropower energy in the rush hours as we need. So it is possible to guarantee we can uniform this load chart, okay, power supply to the grid with several advantages. In the framework of the European decarbonization strategy, it is playing a double valuable role. Hydropower produces clean energy, and its flexible generation strongly contributes to balance the water, energy, and food nexus, the frequency of the power network ensuring grid safety, thus fostering the deployment of intermittent renewable energy sources. Well, here, looking at the renewable energy technologies, they offer opportunities to address trade-offs and the leverage on synergies between sectors to enhance water and energy nexus. However, connecting renewable power plants directly to the grid can cause dynamic controlling problems if the electricity network is not prepared for handling such variations due to the intermittency of renewable sources availability. It can cause some problems, but there is a solution for this. A continuous and reliable power supply is hardly possible without energy storage. Using an energy storage system, the surplus energy can be stored when the power generation exceeds the demand, and then the release to cover the rest period when the net load exists, providing a robust, flexible backup for intermittent renewable energy sources. And we can get a solution using a pump hydropower storage, energy storage solution. Here we can see there is advantage in increasing the system flexibility and reliability, decreasing the variability of renewable sources, since the variable power output can be leveled out due to a complementary nature between renewable sources through their integration in the hydropower by a pump storage solution in a circular economy of water source. We can use the same volume of water between a lower and a upper reservoir as presented in this scheme, and using this same water, we are not wasting water. We can apply here the circular economy too. Well, in this slide, we can see new projects or some adaptations of pump storage systems, for example, in Portugal. We can transfer water from a reservoir created by one dam to another reservoir, depending on the conditions and the quantity of flow available that we have in each system. Here, on the left, we can see the Baixo Sabor power plant, and with 4 reversible groups, we are transforming a simple hydropower into a reversible or a pump storage system. Portugal increased in pump storage hydropower systems from 5 gigawatt to 7 gigawatt by 2020. Another examples of upgrade projects, for example, Alqueva 2, Bemposta 2, and Venda Nova 3, created this type of solutions based on the pump storage solutions. Portugal and Norway leads in Europe the countries that invest more in hydropower and solutions with pump storage. Let's see a very interesting application using another source like floating solar panels in a dam of Alto Rabagão in Portugal too, and here we saw the opportunity using the dam reservoir of hydropower facilities as a pioneer project at the European level, okay? And thanks to the floating solar panels, the occupation of other areas of recognized utility, for example, for agriculture, can be avoided. And it is possible to make use of the connection to the already installed electrical network with higher efficiency due to water serves as a cooling system for the photovoltaic panels, increasing their total efficiency. There is more sunlight when there is less rain, and vice versa, in an excellent complementarity as we can apply also for wind. And we can see here on the left figure, we can see the dam and the reservoir created by the dam of Alto Rabagão. And we can see in the middle the floating solar panels installed here in this reservoir, not occupying other areas that can be used, for example, for agriculture. We can see a zoom of this installation too. And also the flexibility is so big that we can also use the seawater, creating a pump storage power station. Okay, the first one, it was created in Japan, and we can use the lower reservoir as the sea, as an infinite or unlimited water reservoir. But nowadays we are more searching for integrated solutions with different renewable sources, not only hydropower and pump storage, but connected with different other, for example, with wind, with photovoltaic, and also with hydrogen. We can create a symbiosis and a synergies between all of these renewable sources integrated using hydropower solutions. As water resource, we can also use the sea as the bottom reservoir. Well, renewable energies are subject of particular relevance in developed and developing countries. How to store these energies? Well, we need a good and competitive option to store energy generated by intermittent sources. Without storage, the energy produced, if it is not used, it is wasted. Using hydro complemented with a pump storage, this can improve the energy efficiency of the whole system and can generate clean energy without CO2 emissions, significant CO2 emissions, of course, without harming the environment, allowing to overcome the scarcity of resources with the reutilization of the same hydrologic source, this is water, without contributing to global warming. Let's see a real case study. This is a case study developed in Madeira Island. This is one island belong to Portugal. This is the multi-purpose Socorrido system. Initially, it was only an hydropower solution. Initial configuration based only on hydropower. You can see we have here the power station equipped with Pelton turbines, and we have a long hydro tunnels and canals allowing the transfer of water collected from the higher altitude and more pluvious northern sides of the island to the southern side of the island. We have a loading chamber in Cuvão in the middle, okay, of the conveyance system with a maximum capacity of 7,500 cubic meters. We have an hydropower station with 3 Pelton turbines, and we have another one in the middle of our hydraulic circuit. This is firstly a simple hydropower solution. We can see some views, plan views, and of the power station, hydropower station. And with the multi-purpose Socorrido's hydropower system, because you use this water for irrigation, for drinking, for to produce energy in Madeira Island, it started its operation under this initial configuration, allowing the transfer of water from one side to other sides, but only focused on hydropower. But more recently, some improvements come, and it was transformed, this hydropower solution, into a reversible system with addition of some long tunnels, okay, to create some more water storage capacity, and the renovation of some another tunnels, the installation of gates to regulate water flow, allowing the storage of around 55,000 cubic meters of water, creating some galleries excavated on the ground. With these changes, the project objectives were to guarantee more available power, to cut energy losses, to introduce additional wind and solar power, to reduce the use of fossil fuels, because in that place we had previously a thermal fuel power station. It was replaced by an hydropower. So we want to reduce the use of fossil fuels, to reduce the gas emissions, to improve the management of hydropower resources, hydroelectric resources, to increase reliability of the water supply, and to deliver 65% of irrigation water to distribution facilities, to the other facilities, okay, and to have available the water, treated water, for the population. The introduction of another wind farms made possible by the Socorrido's reversible system allowed for a reduction of 28 kilotons of CO2 emissions, 116 tons of sulfur dioxide and 478 tons of nitric oxide and 7 tons of particles, when the replacing by hydropower solution happened. Here we can see the new configuration. New configuration, we can observe a pumping station composed by 4 pumps, 3 in operation, another as a reserved equipment. And we can see here in this scheme what happened. We have some tunnels, okay, on the top, excavated on the ground on the top of the hill. We have a low chamber to make the transition between the flow that comes from the tunnel to the penstock. This penstock feed 2 power stations, one in the middle, Santa Quirite area, and another at the bottom place, the Socorridos hydropower station. And the turbine flow comes to another gallery that can be pumped in other hours. During the day, we are turbining and creating energy, renewable energy, hydropower energy. During the day, we can see we are emptying this tunnel, okay? We are storing the water here in this storage gallery. In order for during the night, we can use the wind turbine to supply, to feed our pumps, okay, to repose or to collect again the water into the upper gallery. During the night, we are doing this. It is completely full and it is ready for another cycle of energy production. Now we have the integration of these wind and solar panels or solar energy, okay, to supply energy, of course, what we need to supply for these pumps. The surplus can be, of course, sell to the electric grid. Well, also Socorridos system affects the daily load diagram. We can see wind and solar photovoltaic penetration is maximized due to the pumping in low peak demands hours, and thermal generation is replaced by an hydro production in peak hours. We can see, I didn't put here, when we have only a thermal fuel power plant, okay, in brick color. But now we have on the left, the load diagram is further smoothed out with the increasing of renewable energy sources penetration of up to 30% of the electricity production share and the reduction of spinning reserves. This results in the avoidance of 100 kilotons of fuel oil importing, which corresponds to more or less 4 million euros savings per year, and to an avoided emission of 300 kilotons of CO2. We can see the difference when we increase between the left and the right picture, when we increase the wind and the pump storage solutions. We can see the pump storage is in red, the wind is in green, and blue, we have the hydropower plants in blue, and it is almost disappearing the thermal contribution. Well, I will show you a small movie. This is about the pumps hydro storage system, which is a type of energy storage that can be implemented with success also in large, medium or small schemes, quite flexible, grid connected or in insulated systems, showing a positive outcome in terms of increased wind and solar energy absorption, while maintaining the economic feasibility of the investment project. The introduction of the pump hydro storage system in highlands, namely in Madeira, Socorridos system, the Socorridos system, as an example, concludes that this type of energy storage contributes positively to the increase in wind and solar penetration and also the hydrogen production. Well, let's see this. I hope we can see. Yes, we can see this is on the left the pumping station. Here on the middle, the hydropower station. The pipe is climbing the hill until to this tunnel. It was excavated on the ground. And we can see we have during the day hours, okay, rush hours, we are turbining, we are producing energy. This is the load chamber in the middle of the conveyance system to make the transition between the tunnel and the penstock. The water that comes from the penstock passed by the turbines and are collected again to this gallery, the gallery of socorridos, in this pumping station. During the night, as we can see on the top, a moon, okay, during the night, we can pump using the tariffs or using the lower tariffs of energy or using other sources like wind, for example. We can pump again and fill again all the tunnel of Covão. And of course, this is ready for another cycle. And another day, we can repeat this. We can see some views of Madeira Island with this penstock. And of course, this transformation in a reversible power station maximizes the hydropower production and energy efficiency, allows overcoming the limitation imposed by the water availability along the whole year, and allows a greater penetration or integration of other clean and renewable energies, such as wind or solar energies. Okay, here we can see the principle of the pump hydro storage solution is to store energy by utilizing the potential energy of water. In periods of low demand and high availability of electrical energy from other renewable sources, the water will be pumped and climb. Okay, I can put the upper reservoir, I can fill it and create potential energy. This is like a big batteries, this water. On demand, the energy can be released, respectively, transformed into electric power within a short reaction time. I can inject this energy in only a few minutes, comparing with the thermal fuel power plants that needs more hours to inject the energy in the grid. Some conclusions. The pumping system can be supplied by intermittent renewable sources with a constant power production using some hydropower solutions, hydraulic turbines. In a hybrid solution, turbines and pumps can be used at the same time, depending on the intermittency, availability, and optimized variables, which include different renewable sources, the storage capacity, and the load demand. We need to analyze all of this using some optimization. If you have only one pipe, of course, it requires different hours. When I'm pumping, I cannot turbine. But if you use two separate pipes, depends on the investment cost, of course, which can offer more operating flexibility. Different sources can be combined, considering different pumps and turbine solutions, combining with other, for example, hydrogen, wind and solar. Hydrogen needs water, and we have water storage there. The surplus energy from renewables produced at times of low demand can be used to store water as a big clean battery and put it ready for release when the demand rises again, with more advantage and greater economic viability also in terms of CO2 emissions or waste released. We don't produce waste, solid waste, with this water battery. A hybrid solution is less expensive considering the power installed with a suitable initial capital costs. Well, additionally, it can be concluded that replacing fossil fuels by renewable energy requires, of course, distributing installations such as wind and solar turbines widely, using a range of different intermittent energy sources, especially those that are partially complementary. For example, sunny weather often means light winds and vice versa, matching with suitable management of energy sources in periods of high demand. And there is clear evidence on how all these modern integrated techniques for complementarity between renewables sources can significantly reduce electricity tariffs and increase the reliability and flexibility of the energy supply as main targets of a hybrid energy solution. The commitment to net zero emissions, we heard some years ago, a summit about this, and the commitment to net zero emissions target has dramatically increased over the last year. More than 120 countries have now committed to net zero targets of CO2 emissions, preventing and controlling the associated climate change problems. And that's all. Thank you very much. I hope you enjoy.
Thank you, Helena, for this wonderful talk. Let's see if my video wants to work now. Okay. We have
I passed 2 minutes from the hour. Okay. I'm sorry.
Okay. We have one question from Liliane. What are the main limitations to having the floating solar panels? This seems like a very interesting idea.
Yes, it is quite interesting. It is new, and we are applying this in a reservoir of Alto Rabagão. It is a big dam, and we have this water, this surface that we can use, avoiding to occupy, for example, lands for agriculture or other uses. Okay, the limitations. It's the anchor. And of course, the fluctuation of the water level in the dam. But as happened with the tidal, as we can imagine, it is quite similar, this situation, okay? When we put these floating panels, the efficiency of this energy is much higher because we can keep more or less constant the temperature around these panels. And of course, this really influenced the global efficiency of the floating solar panels. And this energy produced is near to the system, the electric system of the hydropower, and we can inject into the same. I think there are a lot of advantages. You don't use the lands that we can use for other uses, and the efficiency increases so much. So you are applying this. It is a new solution, and this is another way to integrate in a hydropower system another renewable system, another renewable sources. Thank you for the interest on this. I am also interested on this. Yes.
Anyone else? Okay, we have another question from Ivo Suter. How economically viable is this method? You have to invest a lot of energy to pump the water up, and you argue that it actually lowers electricity prices, potentially leading to lower revenues too?
Well, it depends on the size. It depends on the size. It depends on the characteristics of each system. I published recently in 2020 a paper in Water. We can go to the Water and search for the paper with the name. Something is about pumped hydropower system, and we made some analysis using an optimization model, and with different parameters, depends on the water volume, depends on the number of pipes. If you have 2 pipes or only 1 pipe, of course, if I have only 1 pipe, if I am pumping, I cannot turbining, I cannot produce energy. We have to manage these hours, of course. If you have another complementary energy, like some intermittent energy coming from wind or solar photovoltaic panels, of course, this can be integrated. I cannot say one value because it depends on several factors, but I think with the efficiency of these new renewables and more modern renewables like wind and photovoltaic panels, I think these solutions can be viable and reliable in terms of economic analysis, viability analysis, depending on several factors. But it is a good exercise to make from the small until to large scales, depending on the system characteristics. In some cases, for example, I also developed an interesting study using a water pipe system from the drinking networks, okay, drinking networks. Also, we can use for example, apply some energy devices in irrigation systems. I'm participating in the Red Down project, and we show different applications in terms of the energy production. When we were focused on only to have water for different uses, water uses, and producing a clean energy. Complementing this with a pump storage, of course, a pump, I'm consuming energy, but I am putting available in order to have it free, okay, to when I need this energy, for example, during the rush hours, because if we are using separately, I think in some years ago, we were focused only in a separate energy. We create wind energy, solar energy, hydropower energy. Nowadays, I advise to complement and to integrate all of this in an optimized way. We can turn our systems much more efficient. It is very interesting. This. Thank you very much. I don't have values, but we can search about this depending on the rules and the regulations of each country, of course, and the system characteristics. That's all.
Okay. Well, we also have a question and an answer for Liliane. Mauro Soldati is asking, when are you expecting to release the new impact factors for 2020, the quartiles and etc.?
It has been answered by
yes.
managing editors. Yeah,
I don't know if you want to add anything else.
No, on this, I'm not sure when. I'm not sure if we have this yet, but it depends when we're going to receive the data as well.
Okay. Any other question from the attendees? If not, I think that we can conclude this webinar. Thank you, Helena. Thank you, Liliane, for your talks, for your time answering questions also here now at the end. For every one of you to attending this webinar, enjoy the rest of the day.
Yes, thank you to all.
Thank you, Anna. Thank you all.
Okay, bye-bye.
Bye.
Bye.